It's warm out today. Stay hydrated, people. All right. See, we got problem number 5 written out already, so we can just jump right into it. Let's do it. Okay, problem number 5 says, blah, 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 equilibrium, blah, blah, blah. It gives you all these concentrations. The concentrations are given in molarities, even though these are gases, which I can use a Kp for. I'm going to use a Kc because I was given the concentrations in molarity. So, all right, we know that. Okay, let's see. Blah, 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 blah. Which gases have increased in concentration, which has decreased in concentration at equilibrium. Now, this is referring to a K value. This is at the start, okay? At the start. Okay, starting with these concentrations, which of the gases will increase as soon as we throw them together? Now, what are you talking about? What do you mean by that? Okay, here's what. The equilibrium problems that we've done and will be doing take place after a while. Think back to the Walmart example. You know, Walmart is equilibrium at noon, after people have been coming in and out for a long time. That's when you establish equilibrium. But what if Walmart opens in the morning? It's not equilibrium, right? And what if there was 1,000 people stuck overnight in Walmart? And you had 100 people outside with maybe 100 cats. I don't know, I just made that up. Open the doors, what happens? Will more people go in Walmart or more people go out? We don't know. But at the beginning, we don't know whether or not you throw in a whole bunch of stuff together in your witch's cauldron and get a reaction going, whether or not you throw in so much product that you might actually get reactants to be made. Or you threw in a lot of reactant and not very much product, and you get product made. A Q is a K at the beginning of the reaction. Okay, let me say that one more time. A Q, this problem is referring to a Q expression, is the same thing as a K, except this is after the reaction's been going for a long time and we established equilibrium. This is at the beginning. So this is like you take your, oh, we're here. You take some nitrogen and you take some hydrogen. Got it. Yep, you got it. This is my trusty assistant. I got it. I'm ready. Got my nitrogen and hydrogen. Okay, assistant, your hands are full. I'll grab the ammonia, okay? And on 3, yep, I'm ready. On 3, we're going to throw it into the cauldron and let them react. Okay, I'm ready, said the assistant. 1, 2, 3, throw. Okay, so we throw the nitrogen, the hydrogen, and the ammonia all in at once and let them do their thing. Maybe we threw in so much of this that we're going to get more of this made. Maybe I threw in so much ammonia that I've got an overabundance of it, the reaction goes in the opposite direction and I make this. That's what a K is going to help you figure out. The Q, sorry. The Q is going to help you figure out what's going to happen at the beginning of the reaction. The K tells you what's going on after a while when equilibrium has been established. The K tells us what's going to happen knowing how much stuff you threw in at the beginning. Now, Q expressions are written the same way as K expressions are, so there's no difference there. That's good. So our Q expression for this reaction, let's pretend we're doing a K, because they're done the same way, okay? Products over reactants. Gas, so they all get included, okay? Now, remember, I saw that these were going to be concentrations, so I'm not going to write this as a pressure. I'm going to write this as a concentration. So NH3 squared, exponent 2. Okay, nitrogen, hydrogen, oh, cubed, that 3's a cube. There's my expression. Written for concentrations because I was given concentrations. So let's go ahead and figure out that Q value. Let's figure out what that Q value, and then we're going to go over what does it mean. What does it mean if we get a Q value of whatever I get? Remember, we know what K values, hopefully we know what those mean at this point. Less than 1, that means the reaction does not want to go to the right. Okay, greater than 1, it really wants to go to the right. Okay, if it's a big number. What does Q mean? Let's calculate it first. All right, let's do the math. So, gotta put the numbers in. What was the ammonia? So I'm getting ahead of myself here. All right, the ammonia concentration was 0.48. 0.48. Square that. Divided by the nitrogen. Nitrogen 0.6. And the hydrogen. Hydrogen 0.76 cubic. 0.76 cubic. All right, let's do it and get her done. Get her done. 0.76 times 0.76 times 0.76. I'm cubing the hydrogen first, and I'm going to multiply that by 0.6. 0.2634. Then on top, take 0.48 times 0.48, and get 0.2308. Yeah, they're close. That's actually a little bit less than 1. Let's see what that means. Let's see if I can get an answer. 0.263. All right, we get 0.875. 0.875. Yep, that's what our answer says here, 0.875. Okay, we got 0.875. Okay. All right, great. So I got my Q value, I got my K value for the beginning of the reaction, because remember, they're done the same way. So when we say K means after a long time, we get that value. Q is at the start. So at the start, we threw in, bloop, we threw in that, and that of our hydrogen, our nitrogen, and our ammonia, and we said, go ahead, you guys, do your thing. And we got this value. What does it mean? Okay, over here, I think we can see what it means. This problem did give me the K value. Why'd they do that? Why'd they tell me that the K value is 1.2? Which, by the way, to review, the K value of 1.2 means just barely. These like to go and make ammonia. Now, the thing about ammonia, so something called the Haber process, was the process of speeding up the reaction of nitrogen and hydrogen to make ammonia. It's very important industrially, and over 100 years ago, somebody came up with a way of making this faster, because that is so small. It's just barely above 1, but it just barely likes to go in this direction. So it's not easy for nitrogen and hydrogen to come together and make the ammonia. They do, it's not fast. Okay. That's just what the K value means. I just want to give you a little historical and importance of ammonia production. This Q is less than the K. If the Q is less than K, products are favored. So this Q is less than the K value given, 0.875 is less than 1.2, products are favored. What does that mean? That means that when I threw this stuff together, I threw an abundance of these two in. And you can actually see that from the numbers here compared to that. We threw an overabundance of this and not enough of this, meaning that we're going to make product faster than product is going to break down and make reactant. So remember, we're not at equilibrium yet. We haven't established that. So this is at the beginning. So at the beginning, more of this is going to combine and form ammonia than ammonia is going to break down. Now, after a while, equilibrium gets established and they form each other equally. But at the beginning, because that number is less than that number, we will make more of this than this will break down. All right? I hope that makes some sense. If not, go back, watch the video again. Q values, and K values are super important. We'll be using those for the rest of the course. And K values, or Q values as well. We'll be coming back to Q values later in the course as well. So if that didn't make sense, take another look, and we'll see you soon.